So we've now talked about multiplying radicals and adding radicals and subtracting radicals. So the last operation we have is dividing radical expressions. So we know the radical product rule that says the square root of a times the square root of b is equal to the square root of AB. That's our radical product rule, which says if we're multiplying, that's supposed to be a multiply there, then we can go ahead and put them together, all right, into one radical. Well, that's handy. Well, usually in mathematics, when something is true for multiplication, it's also true for division, and it turns out that it is. Turns out that if we have two radicals and we're dividing it here, like the nth root of a divided by the nth root of b, we can put it together under one radical. Or if it's under one radical, we can separate it into two. All right, works both ways. So we've already kind of seen this a little bit, and maybe we just haven't spent too much time on it, but what that does for us here is we can take these two radicals that are being divided, and we can put them under one radical. Okay, this is our radical quotient rule. And when we put them under one radical like this, then we can simplify it. And that's going to make our life simpler, thus the name. All right, so now just ignoring the square roots, it all lives under the square root, but we're going to go ahead and do some simplifying. 48 divided by 3 is 16. And x cubed divided by x squared is x to the first. And y to the eighth divided by y to the second. Remember, we subtract the exponents. That's y to the sixth. All right? Then we've got to ask ourselves, can we simplify this? So we're going to break it up into things we can simplify and things we can't. We ask ourselves, is there a perfect cube in 16? There is. It's 8. 8 times 2 is 16. I could do the cube root of 8. That's going to be 2 in a second. I got x to the first, so just a single x. We can't simplify that. That's not going to come out. But y to the 6, since the exponent is a multiple of the index, can be simplified. We'll do 6 divided by 3. This is y squared to the third power. All right. So we have 6 divided by 3. Well, first of all, the cube root of 8 is 2. And 6 divided by 3 is 2. Okay. There we have it. Okay. All right. Well, now we run into a situation where we want to have no square roots in the denominator, and we call that rationalizing the denominator. So rationalizing the denominator is the process of writing an equivalent expression in which the denominator is rational. In other words, no square roots or any irrational roots in the denominator. Okay, specifically talking about the denominator. All right, so let's see how that works here. Okay, so the directions are we want to rationalize the denominator. That means we don't like to have this square root of 2 down here. Now, by the way, can we divide this 6 divided by 2? No, we can't, because this isn't a radical, this is not. So, think about that. You might think, well, maybe we could square the top and square the bottom. Well, unfortunately, we can't do that. Not allowed to do that to a fraction because that'll change the value. All right, if you have 1/3 and you square the top and square the bottom, that gives you 1/9. 1/9 is not the same as 1/3. So this is no good. You can't just square the top and the bottom. Well, that's a good idea if you had that thought. Well, why does squaring help us? Well, squaring help us because I'd like this to square or to multiply by itself. So I'd like to multiply the bottom by the square root of 2. Well, we are allowed to multiply fractions by the square root of 2 on the bottom if we multiply the top by the square root of 2. Right? So we've got to multiply top and bottom by the same number. Because what is this really worth? This is a very important concept. Square root of 2 over the square root of 2 is really just worth 1, right? And when we multiply a fraction by 1, a big fat 1 there, it doesn't change anything, because multiplying by 1 doesn't change a number. Well, it doesn't change the value, I should say. So let's go ahead and multiply it. On top, we get 6 times the square root of 2, which we can't do anything with because 6 is out of the radical, 2 is in the radical. And we get the square root of 2 times the square root of 2, that is the square root of 4. Well, we know the square root of 4. The square root of 4 is 2. Now, we have these things outside the radical. Don't go try to divide these. This is under a square root, this is not. You can't combine those in any way. But we can simplify these here. We can do this 6 divided by 2 there. That's going to give us 3. And so we end up with 3 square root of 2. So the moral of the story is this. 6 square root of 2, 6 divided by the square root of 2 is the same as 3 times the square root of 2. And so we can check that out. 6 divided by the square root of 2 here gives us 4.2426. If we have 3 times the square root of 2, we end up with the same number. All right, so that's handy. All right, so moral of the story is those are equivalent, and we just like the fact that this has no denominator. It's easier to work with, all right? Okay, let's work through some examples here, all right? So here we can do a little simplifying with that 2 and that 6. Well, I might as well do that. That gives us 3 on the bottom. 2 of these cancels with 2 there. Divide top and bottom by 2. Okay, now let's go ahead and break it up. We don't want to have a square root in the bottom, so what do? We multiply by that square root. And we end up with, on top, we can multiply those. X times 3y is 3xy. And on the bottom, we have the square root of 3 times 3, which is 9. Y times y is y squared. And we can simplify that. Basically, notice we're just squaring 3y, the square root of 3y. When we square the square root of 3y, it's going to make that radical go away. So we're going to have 3xy on top, under the radical, and 3y underneath in the denominator. Again, don't try to simplify those because these are under a radical, these are not. Okay. What about cube roots? Well, cube roots gets kind of interesting here. We can't simplify anything there, so we break it up into the cube root of 2 over the cube root of 25. And this is useful here to factor the cube root of 25 into 5 squared. Okay, 25 can do is 5 times 5, 5 squared. Okay, what would you like this exponent to be? Well, we would like it to be a third power, right? I'm going to clean that up. Okay, we'd like that to be 5 to the third, then we just cancel. So what do we need under here? Well, we need another factor of 5. And so we're going to multiply by the cube root of 5 to the first. And what you multiply the top by, or the bottom by, you got to multiply the top by, right? And so notice we're doing cube roots. Everything's cube roots in this problem. 5 to the second power times 5 to the first power. Just think of this like an x. X to the second power, x to the first power would be x to the third. So in this case, 5 to the second power times 5 to the first power is 5 to the third power. Don't multiply that out. We don't need it multiplied out. The top is 2 times 5. Well, that one we're going to multiply out. 5 times 2 is 10. All right. And so the bottom, the cube root of 5 cubed, that now just cancels because they're opposites. And so we end up with the cube root of 10 on top and 5 on the bottom. See how that works? So in this case, we're not multiplying by exactly the same, but we want to get that third power. Okay, you might try that if you want to. You can try this one. You might want to pause and try that out. See what you get. We're not worried about the top at all. Just totally ignore the top. These are cube roots, so watch out. We would like to deal with the bottom. Now the bottom, let's write that in factored form. That's 2 times 2, which is 2 squared. All right? We'd like that to be 2 to the third. So what do we need to multiply by? The cube root of 2 to the first. Multiply top and bottom by the same thing. On the top, we have 9 times 2. That's just 18. On the bottom, we have 3 to the third power, because it's, I'm sorry, not 3, 2 to the third power. Okay, because we have 2 to the second times 2 to the first. That's just 2 times 2 times 2, which is 2 to the third, which is nice because that's going to simplify to 2. And that's it. We can't simplify this because there's no perfect cube. Perfect cubes are 1, 8, 27, so on and so forth. They do not go into 18. Okay? All right. Well, let's throw some variables in the mix here. Again, we don't care about the numerator, so just ignore that. We'll just let the numerator get ugly. We would like to take this 9 and write it as 3 times 3, which is 3 squared. And y. I really like to write this in this exponential form. You'll see some other videos where you'll write 3 times 3, and we want to have 3 3's in here. This is a much better way if you can handle that. Because we want that exponent. We're comparing that exponent to that index. We want that to be 3 in the exponent, so it cancels. So we need to have 3 3's, but we only have 2 3's in the mix. Okay, so we need a 3 to the first, because 3 to the second times 3 to the first is going to give us 3 to the third, and that's good. We need 3 factors of 3. We also need 3 factors of y. We only have y to the first, so we need a couple more y's. That should do it for us. Now what we multiply the bottom by, we need to multiply the top by. 3 to the first times y squared. Okay? So we're multiplying by a special form of 1. Now watch what happens. The bottom's going to become, and let's see, how many 3's? 3 squared times 3 to the first is 3 to the third. Y to the first times y squared is y to the third. And that's nice because these 3's are going to get canceled out by that index, just divide it out, right? On the top, we've got 3, an x, and a y squared, and we just kind of multiply them all. We can multiply them. Remember, we can squeeze things under one radical because we're multiplying, not adding. Then last step is to clean up the bottom. The whole point here was to make this without a square root, and that's a 3 and a y because that canceled those out, right? And the top is the cube root of 3xy squared. Multicolored answer there. All right. How about one more? 5th root. Okay, a lot going on here. But if we factor that 8, 8 is 2 to the third power. So this is the 5th root of 2 to the third power, x to the third power, y to the 4th. What would you like each of these exponents to be? You want them to be 5, right? I'd like this to be a 5, this to be a 5, this to be a 5. And then it would all just cancel. So we need some more ingredients, all right? Think of it like a recipe we're making here, right? You need some more ingredients. What would you like? We need some 2's. How many more 2's do you need? I'd like this to be a 5, so I need 2 2's. Good for ballet, right? How many more x's do you need? We need 2 of them. Okay, not so good for ballet. How many y's do we need? We have 4 of them. We're going to the store. We'd like this to be 5, so we need 1 more y. Okay, so we've we've decided what we need on the bottom. The top is going to be identical. Again, we don't care about the top. The top's going to get ugly. We don't care about that. The top, in fact, is going to be 6x times the fifth root of 2 squared, which is 4x squared y. The bottom is going to be the fifth root of 2 to the fifth, x to the fifth, y to the fifth. Because we're multiplying these, so we add the exponents. 4 plus 1, 5. Okay? And notice these are all the fifth root of a bunch of fifth powers. They all cancel. 6x times the fifth root of 4x squared y. And these are just 2xy. Okay? All of these get fifth rooted. And that's why they get to come out of the radical. No more radical in the denominator. That's the whole goal. We have rationalized the denominator. All right?